this is the last thing that we did last time. I think this is kind of a nifty little result. It says that if you have abelian is very important. Group order P to the n, then it's cyclic if and only if G has one and only one subgroup order P. Of course, if it's group order P to the n, it has to have some subgroup order P. If it's cyclic, this is true because we've seen that there's one and only one subgroup for every order by, or for every number by the order. And we proved the other way last time. This is going to help us a bit. In particular, suppose again that G is an abelian P group and H is a cyclic subgroup of P of maximum order. So let me emphasize this. Let H be a cyclic subgroup of G of maximum order. You might sort of comb through G and find the largest cyclic subgroup. But this is equivalent to looking through G and finding an element of the largest order. Then you can pull out that subgroup of maximal order with some other group. So what this says is if G is any abelian P, let's suppose it's order P to the n. Suppose that P to the m, you find an element in here of order P to the m, and that's as big as it gets, right? There is no element of order higher than P to the m. And that means that cyclic piece, this subgroup order P to the m, pulls out as a direct summand of G. So you can find some other subgroup that when you put those two puzzle pieces together, you get G. Let's see why this is true. Suppose if the order of P to the n, we go by induction on n. And we will make this non-trivial, so we will start with case n equals 1. Tell me, okay, what happens if G is already cyclic? What can you take K to be?
Well, K will be the identity of it.
You could, that's right, in a very silly way, if G itself is cyclic, then this thing right here is G. It's the biggest cyclic subgroup, and this thing would be just 0. Right. So this is sad in one case, because if the order of G is G, then E. So no problem there. So let's start to climb the ladder. Now, send result holes for all abelian P groups of order P K, or K less than three, so, yeah. And now we're gonna look at the plus one case. So suppose again, let me make a remark that if this is cyclic, we're done. Because G is its own largest cyclic subgroup, and you can take K to be the zero subgroup. If not, then what do we know from 721? What do we know from last time? If G is not cyclic, there have to be at least two subgroups of order B, right? Because that was our condition for it being cyclic, is it was one and only one subgroup of order B. So there have to be at least two. Two subgroups. G of order.
That's the theory to discuss.
Um, so I'm gonna kind of build these up this way. Let H maximal order. Of course, such a thing should exist because there's a cyclic subgroup of order P for sure. Right? And so all you have to do is just go through it. Is there one of order P squared? Is there a one of order P cubed? This is a finite number of things to check. Whatever's the maximal one, that's going to be H. H may not be unique. There might be several subgroups of the same word. Just pick one. It doesn't matter. But let me point out that H contains a subgroup of let K be another subgroup. Notice that since H is cyclic, H only contains one subgroup for B. Any cyclic group only contains one subgroup for every five of the order. So we picked another one, K, that must exist, and K is not equal to that subgroup of H. Now, H intersect K must be zero, because if that's not the case, that means the K is contained in H. So that's cyclic for P, and it would have to coincide with a subgroup of order P. So it must be the case by the way, anybody remember what this is isomorphic by the one of those isomorphic theorems, the second, I think. This is modulo,
H index, okay?
yeah, intersection. But the intersection here is zero, right? There's no intersection. This is actually that's not the page. Now. Yes,
Using a plus there instead of direct product, just because.
this is all Abelian. That's right. That's the more common notation to use when the group is in fact Abelian. The code set G plus K has order dividing G. This may be a little bit hidden, but this is a result essentially from the homework, because there's a homework. There's a, we know that there's a homomorphism from G to G mod K. And the image of G is the cell here. And since this is a homomorphic image of G, that means the order of this has to divide the order of the original G. This is a homework question that we had earlier. And the order of G is less than or equal to. Why is that? Well, because H is a subgroup, cyclic subgroup of maximal order. And so if the order of G was bigger than the order of H, then G, that G should have been generated as maximal cyclic subgroup. Okay, everybody with me so far?
Yes.
Hence, the subgroup H plus K, mod K, which is isomorphic to H, has maximal order in G, mod K. And this allows us, to imply the inductive hypothesis. Because notice, the order of G was M plus 1. The order of G mod K is P to the M. Because the order of the subgroup K is just an order P to the M. Oh, I'm sorry. This is for P to the N plus 1. This is for the quotients has order P to the N plus 1. Okay, so what does the inductive hypothesis allow us to do? So we can now obtain a group now. Why? Inductive hypothesis. Find a group. I'm going to call it N mod K, G mod K. Of course, I'm implicitly here using the third isomorphism because any subgroup G mod K has to take mod K, where N is implicitly a subgroup containing K and containing K, right? Isomorphic this S. This is the cyclic piece. So there's our inductive hypothesis working for us. So let me take this apart. So anything in G, you can write as H plus K plus N. Some choices of H and K and N, and I can abbreviate that even further because K is actually an N. Notice that so we're almost there. We've got, at this point, we've got G is a sum of H and N. That is, everything in G can be written as something in H plus something in N. Right? What else do we have? Notice that N intersect H plus K should equal K. Why is that case? Because this right here, our inductive bit, this is a direct, well, I call it direct sum here, direct product, whatever you call it, decomposition. That means that the intersection of these two pieces is trivial. And when I say trivial, I mean trivial in G mod K, which means the intersection of this is K. And so this means that N intersect H is equal. And this follows from H intersect K is 0 as well. So, right. And so what that gives us is G equals A plus E, that is H and N generate all of G. And two, you know, in the statement of all this garbage about direct products and so forth, we had those normality conditions, and none of that's necessary here. Because our groups are all Abelian, so every subgroup is normal. So therefore, G is isomorphic. H stomach. And there we established the inductive. Yes.
Wait, zero, by the intersection, zero, that just be identical.
Yeah, that's right. Yeah, that's it. Because our group's Abelian here, and so I'm writing 0 to the active.
And then also, what's the difference between, because I know that's the direct sum, but what's the difference between that and like the regular plus, like? the
Okay,
circle?
right. Okay, yeah, I thank you. What this means is that everything in G can be written as something from H plus something from N, right? This means the direct sum means that that representation is unique, right? So this plus the intersection of these two being 0 gives you a uniqueness of representation. So this means I can throw together any element, elements of H and N, put it together and get all G. This means that it's unique. It's actually a direct, in this case, sum decomposition. Okay, any questions? Okay. One last stair step, and then I want to give you the fundamental theorem. Well, essentially. Proposition. Let's let G be a finite abelian P group. Then G is uniquely a direct product or direct sum of cyclic B groups. Yes, so that's really cool. If I could walk up to you on the street, and if I give you a finite abelian P group, then you can write it, in fact, uniquely as a direct product of cyclic P groups. So you can always decompose it into this product of cyclic groups. Why is this true? Proof. Suppose order P is the N, and again, I'm going to go by induction on N. This is probably an easier induction than last one. For the case n equals 1, that means the group is prime ordered, is cyclic. And so it can certainly, the group's isomorphic to ZP. There's only one way to write that, is cyclic group ZP itself. You're done. You get uniqueness the whole from here. Now suppose that it holds suppose results holds for all abelian groups of order pk so suppose it holds for all powers of the groups of that order all the way up to the nth power. Now suppose that G is the order of G is n plus 1. Again, if G is cyclic, we're done. If not, then there exists H and G, maximal cyclic subgroup. And so the order of H is P to K, where K is less than, less than or equal to. What do we know from our previous result? Well, from our previous result, we know that there exists K and G such that G is isomorphic H. Now what?
Now when you say it's K is cyclic.
Right.
Because H is cyclic, so it becomes trivial.
I agree. The order of K is the order of G minus to the power Well, the order of K is the order of G divided by the order of H, which is P to the N plus one minus. And notice that since K is at least one, this is strictly less. So inductive hypothesis. Applies. Okay. So write K as let's see, H1 HL with E H I similar. So G is isomorphic to H, direct sum, H1 direct sum. Where you have to H level. So there's our decomposition into cyclic figures. I did not prove uniqueness. Give that a try. See if you can glean why it's unique. We're almost there if you assume uniqueness is part of the inductive hypothesis, but why does it matter for the H? Okay. Before I do the classification, any questions of stampede? Corollary. Any finite abelian group is a direct product, a direct sum, if you like, CLS. Abelian is terribly important here. Is a direct product. All right, sum here. It's zero in preference. Okay. Suppose P1 to Pn are zero PI subgroups of T and his billion. So PI is PI group. And P1, P2, Pn are prime. Right. You. Okay. Notice, by the way, I remember from the CELO theorems that so for example, P1 is the CELO P1 group from first prime, right? I noticed in the CELO theorems, I can sometimes have several CELO P subgroups corresponding to the same prime. Right? If you look at S3, there are actually 3 CELO 2 subgroups. All right. Why have I just listed one for every prime? Back under our hypothesis, there should be only one CELO P subgroup for every prime G. Why is that?
They're all here.
Correct. G is an abelian group. And any subgroup is normal. So all these CLO subgroups are normal, correct? So there can only be one of them. Do I go to that? Notice that okay, this is back, so this is your question over. I do mean plus without the little circle around. Notice everything in here is the sum. Now, wait a minute, I'm playing a little bit fast and loose here. Why? Can somebody explain why this is true? How do I know that everything in G is sum of the CLO P subgroups? How do I know?
Probably perhaps like you do then all kind of multiply together to make into here something. I guess it's kind of not right, because you could probably have like hours of P1 or P2 in there.
Okay, so let me ask you this. How many elements are there? And let's just start with this case.
So from P1 plus P2, so it's going to probably be something like that. P1 plus P2, and then of course over the intersection, which is probably 0 to square direct equals P1 P2, you know?
Everything in here is for power of P1, everything in here is for power of P2. This is one. Inductively, notice that the order of this is the highest power of prime P1 that divides over G. This is the highest power of prime P2 that divides over G. This is the highest power of prime P in the end that divides over. So this should actually be accepted. So just by counting the elements, of course, this thing is contained in G, but it's got enough elements in it to be all of G. So that's what it is. And for all I between 1 and n, Pi intersects with P1, P2, Pi minus 1, Pi plus 1, Pn is equal to 0. The active item. And again, this is very much the same. If you look back at what we did here, the order of the subgroup generated by this is relatively prime to Pi, right? And so that means that nothing in here has order of power of Pi. Everything in here has power or power of Pi, so it's intersection. And so that gets what we need, because we know that all the CLO P subgroups generate G. And number 2, we know that it's a direct sum because the overlaps of all the others. And there's okay. Any questions? Yes.
So what about G just
I can tell you what the order of G is. So that's my notation. This is a CLO. This is a CLO PI subgroup, and it's got some power here. MI is at least 1. So the order of G is the order PI. just like that. Basically, product of all the elements of the single surface. Okay, so I'm gonna write this theorem down here. Let's start. So I'm gonna write this down, and then I'm gonna do a couple of examples to really kind of illustrate. This is something that I almost guarantee you that I'll ask you to be able to do a problem like this on the next exam. Theorem. So I'm gonna do this just for finite groups first, and then I'm gonna give you a more general thing here. Suppose that G is a finite abelian group of order n. Finite, or no, a finite abelian group. Of order n. Then G can be decomposed as follows. I'm gonna give you two ways to break down. Number one, and this first one is called the elementary divisor decomposition. As a correct product. Sigma groups. And products, product of these orders. This is called the elementary divisor. So you can either break it up into a product of which things can power, or you might choose to go a different route. A direct product of cyclic subgroups. Not necessarily this kind of compound of this form. Where where sigma order mi, and I further will stipulate where the order of this divides the order of this, the order of this divides the order of this, and so forth. So it's like a successive. This is called the invariant factor. Decomposition. And these MIs are called the invariant factors. Both of these decompositions are unique up to commuting the groups. Yes,
Just that second part, so saying M1 is dividing into two? Or
that's right. M1 divides into 2, which divides into 3, all the way up, like that. Let me give you a sentence. I don't know much, but I know Z6 is cyclic, right? This is already its own invariant factor decomposition. It's already set. Elementary divisor. The primes that divide 6 are 2 and 3, and this is C2 something. Let's do 1. This group is not cyclic. It's more than 240, and there's no. I'm gonna take this apart. This one's got a little bit more teeth. I'm gonna do it really good. Six. That's 2 squared times 3 times 5. By the way, this is already in invariant factor decomposition as well, right? Because 4 divides 60. So this is in. Only I've got it in the other order that I have it theorem. I had Z4 corrects and Z6, but everybody agrees that 4 divides 60, so work, right? What is the elementary divisors? Well, I've got 3 primes to divide this. This is actually, and this is a trick, follow from some stuff we've done. But again, the follows the properties of the integers. I can decompose, since these are relatively prime, as to Z2 squared, Z3, Z5. And this gives me my elementary divisor. I'm going to do this by primes and divided. There are 3 different primes that divide the order of this group, 2, 3, and 5. With a 2, I get 2 copies of Z4, and then 1 copy of Z3, 1 copy. Right? Yes.
So why couldn't we have bring the very factor calculation? Even if it had C2 plus Z2 plus 260, that would still follow the formula.
But that's not isomorphic to Z2 and Z2. That's the problem. Where I'm keeping the isomorphism price the same. Z2 is a group of order 4, but there's no element of order 4 there. Okay, so you can't break down the prime power further. Let me give you one. Yes.
You combine the 2 different Z2 squares?
No.
No.
You mean like Z16?
Yeah.
No, you can't do that because Z16 has an element of order 16 in it, but Z4 directs from Z4 has no element of order higher than 4. Let me give you one with some teeth to this, and this one I think I'll help you out. I do this. What if I want to write the invariant factor decomposition and the elementary divisor of the following? 24 plus 5. Um. Okay. So I want to find this. So the first thing to do is factor these stupid numbers into prime powers, and that's what I'm going to do. So I'm just going to write this here. 108. All right. That's like what? 27 times 4 maybe. So that's 2 squared times 3. If I agree with you. You better check the math on that. This is 2 cubed times 3. This is horrible. That's probably 5 cubed times 3 squared, I guess. This is 2 squared. It's 3, 5, 7, I think. And this is 2 squared. Uh, 5. Everybody agree on this? So the first chunk that I'm going to do is you can do this in either order. If you're clever, but the first thing I'm going to do is I am going to group this. I'm going to do elementary divisors first by just moving prime. I can break this up here. Z4 sum Z27. This is Z8 direct sum Z3. This is Z27, Z125, Z4, Z3, Z5, Z7, and finally this last straggler here is Z4, some Z5, some Z31. Everybody okay with that? Now, the first thing I'm going to do is I'm basically just going to write down my elementary class decomposition. Elementary divisor. And I'm going to group this by. Two is the first prime I come to. What's the highest power of 2 that I ever get here? I guess it's 8. Everybody agree with that? So C8, I got you taken care of. I've got a Z4 and another Z4 and another Z4. So I had 3 of those. Everybody okay with that? All I'm doing is I'm going through them, and I'm getting decreasing order, right? Z8, Z4. Everybody okay with that? Next prime, 3. See what I've got here. What's the biggest power of 3 I've got?
27.
Looks like. And how many do I have? I've got 1, 2. What else do I have? Any? I've got a pair of Z3s, don't I? Yes.
Is there a reason why? Is there a reason why we're thinking of parentheses of reordering them? Does it sort of matter here?
No, but it's going to be convenient for me to do next. There's a pair of these, right? And that takes care of 3. Next prime I come to is 5. Okay, your way, your way. What do I got for 5? I've got a 125. And I got a pair of 5s. Everybody okay with that? 3, 4, 6. Then I've got 7. Two of those. Actually, no, I don't. Do I?
A single one.
I've just got a single, don't I? And then I've got a Z31. There is your elementary type. Let's do the invariant factor. And Henry, this is why it is. Go through and pluck off the primes that are, pluck off the biggest that you can. Z 8, 27, 125, 7, and 31. So this is Z to the, who knows what it is, 2 cubed times 3 cubed times 5 cubed times 7 times 31. That is the biggest sequence factor right there. It's putting all the biggest ones back together. All right. So I'll snap this back together since they're relatively prime, it just multiplies. Next term, much more modest. Z4. 27. Z5. And then you're out of real estate, right? Next one. Z4. Z3. Z5. There's the Z60 in there. And finally, your last one, Z4. And that is your, that's how you compute from that, the invariant factor. Any questions on that? Notice that this divides this, this divides this, this divides this. So this is, I've got these down in 4 cyclic factors. This one's more convenient because if you like prime powers, because these are all prime powers, so then that's good. But notice here I've got 13 cyclic factors. And here I've only got 4. So depending on what your application is, you might want a little more. Everybody understand how we did that?
Yep.
Okay, any questions? All right, I will see you folks next.
I believe the proof we covered on Wednesday, right?
I'm sorry,
Will the proof for this be covered on Wednesday?
we've done it.
No.
It's all done already.